how's it going, guys? This is a very simple lecture, this chapter 10 lecture. Just want to go ahead and get it recorded and uploaded so you'd have more information to go over as time progresses, sooner rather than later. Alright, really a basic lecture. So this is basically an intro to smooth muscle and sort of how it works. So smooth muscle is a little different than skeletal muscle. So if chapter 9 is basically focusing on skeletal muscle, this is basically a talk on smooth muscle. Smooth muscle found in the walls of hollow organs. Think about like the intestinal tract, or the stomach, or the bladder, or any of these locations. You're going to find smooth muscle. Normally it comes in two layers. What you'll have is one layer that forms like a sheet around, we call it circular muscle, around a tube like the intestine. And then a sheet called a longitudinal layer that runs sort of backwards and forwards through the tube. So there will be a sheet that comes in a circle around the intestine, and then a sheet that runs from left to right, so to speak. So longitudinal and circular layers. Now, smooth muscle has a very, very slow ATPase. It contracts very, very slowly, and as a result of contracting quite slowly, this also means that it tends to have a very low fatigue. It's very hardy. In other words, smooth muscle can contract and remain contract for prolonged periods of time. It does not fatigue readily. And while I'm on the subject, that might be the next slide, but you'll notice that smooth muscle cells themselves have this sort of point on each end, fat in the middle shape. The term eludes me at this particular stage, but the idea is that they are non-striated. Internally, you do not see these patterned striations. There's still actin and myosin interacting here, but you don't see these patterned striations. Alright, longitudinal layer and a circular layer. And the idea is that by having a longitudinal layer, what you can do is, it's hard to explain here, but what you can do is you can squeeze off a tube, or alternatively, with the circular and longitudinal layer, you can change the length, okay? And what this really leads to, having the ability to close the tube and to change the length of the tube, is this leads to a concept we call peristalsis. Peristalsis is a set of rhythmic contractions that propels materials down the length of the tubes of your body, alright? Your ureters do this, is a good example. So, if you were to be hanging upside down by your feet, you would still fill your bladder over time if you're drinking fluids, because the kidneys produce urine, and that is pumped. It's pumped with the ureters to the bladder. So what will happen is, the tube will close off at one end, like this, and then the contraction wave will flow down the length of the tube. So you end up with these sets of rhythmic contractions, which propels materials down the length of the tube, almost like an earthworm crawling, okay? That is peristalsis. And you can somewhat see this here. This is a ring of musculature, and you can see the ring moving down the length of the tube. That is peristaltic motion. Alright, there are two formats in terms of smooth muscle. What's called multi-unit smooth muscle and what's called unitary smooth muscle. Multi-unit smooth muscle tends to act a little bit like skeletal muscle and cardiac muscle. You'll have individual cells with individual neuron connections, individual synapses. So the nerve comes down, it synapses with the muscle. The nerve stimulates the muscle directly. It's a lot like every other system in your body. Here, here in multi-unit smooth muscle, gap junctions and spontaneous depolarization are quite rare. What that means is the muscle has to be stimulated by a neuron to contract. There are no gap junctions linking together parts of the tissue. In unitary smooth muscle, this is different. Unitary smooth, and by the way, multi-unit smooth muscle, this is going to be in like your rector pili muscles. In the iris of your eye, where you need real delicate control, that's where you find multi-unit smooth muscle. Unitary smooth muscle is different. This is like what you find in your intestinal tract, in your stomach, in your ureters. Here, instead of having traditional neuron, axon terminal, synapse, muscle setup, what we have is what are called varicocytes. We've got all of these individual smooth muscle cells that are all linked together via gap junctions. So if one fires off, they all contract. And instead of being innervated via a synapse, what they have are varicocytes. And when I think about varicocytes, Yeah, I think about crop dusting. So what, like a crop duster flies over crops and broadcasts a chemical or what have you onto those crops. These varicocytes will broadcast neurotransmitter all over these cells, stimulating whole areas of the tissue as a unit. As a unit. Alright? One whole area of the tissue stimulated as a unit because the varicocytes broadcast that neurotransmitter over the entire area. So yeah, this is a little bit different. So here we have cells which are linked via gap junctions. They work as a single unit. This is again like your ureters, like your small intestines. That's you can feel oftentimes what are referred to as mass movements of your intestinal tract. So you can feel these contractile, peristaltic, contractile waves. You'll feel them start at one spot on your stomach and kind of move to the other. What you're feeling there is those muscles contracting in a wave because of the smooth muscle being linked via gap junctions. So when these start to go, the wave just flows down through. Alright? Whole areas of muscle. Peristalsis. Alright, a special feature of smooth muscle is hyperplasia. Smooth muscle cells are capable of mitotically dividing and growing in number. A great example of this is the uterus in pregnancy. So the uterus itself is quite small, much smaller than my hand. Okay, very, very small. But during pregnancy, the uterus must get quite large indeed to house a growing fetus. I mean, it's a big structure. So to enable it to do this, the smooth muscle found there is capable of dividing and increasing in number. Alright, let's move on to a little bit different concept. What I want to do is talk a little bit about muscle tissue and how we name it and sort of how all this is put together. Alright, naming of skeletal muscles. And I feel like we sort of played this game in lab, but I think it's worthy to do it one more time in lecture just to make the point. So sometimes we name muscles based off of their location. Like intercostal. Anything costal is going to deal with the ribs, so the intercostal muscles are found between the ribs, muscle locations. Muscle shapes. Trapezius muscle looks like a trapezoid. Deltoid muscle looks like a triangle. Delta is a letter, alright? Muscle size, maximus. Anything maximus is large. Brevis would be short. Longus is long. Minimus is small. Like, these are just terms that we use as descriptors to name muscles. Again, direction of muscle fibers. So muscle fibers, which are rectus fibers, tend to run straight up and down the body or in direct straight lines. Transversus fibers run on angles, so kind of straight across, whereas obliques run on angles like this. So rectus would come straight up and down, transversus would go straight right to left, and obliques come on a weird angle like so. Alright, I think we talked about origins and insertions, but the idea is that the origin of a muscle does not move when you contract it. So if you contract your bicep, you'll notice at the top at your shoulder, it does not move, whereas the insertion point down at the bottom does in fact move. Okay, so that's origin insertions. The origin tends to be non-mobile, whereas the insertion point is in fact mobile. Alright, we name skeletal muscles based off of their number of origins. The reason we call the biceps is because it has two origin points. Sepes, anything seps, means heads. So biceps means 2 heads, triceps means 3 heads. So the number of origins. We name muscles for their locations of attachment. Again, one of the best is the sternocleidomastoideus. Starts at the sternum, goes to the clavicle, runs up to behind your ear where the mastoid process is. Brachioradialis starts in the brachial region of the arm, goes down to the radius, I should say, as its insertion point. We can name muscles based off of their actions. Like all of these muscles here are considered flexors because they flex the carpals down. And back here, all these muscles are considered extensors because they extend the carpals. And then we can combine several of these criteria together. So extensor carpi radialis longus, extensor carpi radialis longus. So it's a muscle right in there, right on the top of my arm. Alright. Fascicles and muscle shapes. So what this is really doing is we're playing a game with the ability to change length over time versus the ability to attain strength. Okay, changing length over time versus attaining strength. Your bicep, as an example, you would think of your bicep as being quite a strong muscle. It is not. It is strong just based off its general size, but it's not built, like the way it's designed is not for strength. Muscles that are designed for strength look more like this. Okay, like your deltoid. It's capable of generating massive quantities of force, even though the muscle itself is not as large. By packing in all these sarcomeres on angles to connective tissue. You pack in way more sarcomeres in a muscle that looks like this, these pinnate or multi-pinnate muscles, compared to a fusiform muscle like your bicep. Here, all the muscle fibers are running at length. Okay, they're running lengthwise, whereas here the muscle fibers are coming in on angles like this. Because the muscle fibers here are all parallel to one another, this makes the bicep capable of changing length over long distances. Whereas muscles here, like pinnate muscles, they don't contract for as much length. The idea is that they are capable of incredible strength by comparison. And then, interestingly, we have these orbicular muscles like this, orbital circular muscles, of which you have a few. You have an orbicularis oris, which is what closes your lips for your mouth, and an orbicularis oculi, which allows you to close your eyes. And by the way, pinnate means feather-like. It's supposed to look like a feather. Alright, in any muscular contraction, there will be what are called prime movers, synergists, antagonists, and fixators. Prime movers are the muscles which do the majority of the work. So when the muscle contracts, or when you do a job, when I pick up the remote for this screen here, the prime mover would be my bicep. Okay, my prime mover, my bicep, does the majority of the work. Synergists help. They assist with the process. They are synergists. They help. Antagonists work against the action of the prime mover. So if the prime mover is my bicep there, the antagonist would be my tricep. And what the antagonists tend to do is they slow things down and make muscle flexions more controlled. And then last but not least, there are fixation muscles or fixators, like the rhomboids, which attach to your scapula. And what they will do is they'll just lock everything down in place so that the arm is held quite tightly to the body while you're doing whatever it is you have to do with that bicep and tricep and what have you. So fixation muscles sort of hold everything together. Alright, there are intrinsic muscles and there are extrinsic muscles. Intrinsic muscles are those which do their job in the location and the region where they're found. Extrinsic muscles have big long tendons and do their job elsewhere. Let me give you a good example. Alright, the muscle that runs my thumb, that allows me to move my thumb like so, it's right here. Alright, it is on my thumb. The muscle that runs my thumb is on my thumb, it's all together. But the muscle that runs my pointer finger is way down here. Okay, you can stick a finger in there and you can feel in your arm the movement of the muscles way down here that have a long tendon that go all the way up your finger. That would be intrinsic muscle versus extrinsic muscle, way down here. Alright, blood supply. So, let's see here. You know that your muscles get massive quantities of blood flow. That is a fact. We probably should talk about numbers. So your muscular system receives about 1.24 liters of blood per minute. That is 1/4 of the blood pumped by the heart. During really extreme exercise, you can increase this greatly. You can put about 3/4 of the blood pumped by the heart into the muscles. And the question is why? Because in emergency situations, our muscles need to keep working. So we need to keep getting flow to the muscles. If you're running from a tiger, you need to make sure that you got plenty of blood flow to your muscles so that you can keep them functioning. And this blood normally would be, for instance, like in your digestive tract, but you're capable of pulling this out and putting it into the muscles in case of emergency. This would be considered a sympathetic nervous system response or a fight or flight response. And we'll be talking more about that in just a little while. Alright, hernias. So a hernia is any condition where viscera protrudes through a weak point in the body wall. Let's see. Factors contributing: heavy lifting, poor posture, mechanical impacts, pressure. Diagnosis: bulge of the skin. Alright, these are very prevalent. Very, very prevalent. You know, I'll never forget when I was a kid, hearing my grandfather talk about, oh yeah, I got these hernias. You know, I push them back in and then sometimes pop right back out. Terrifying. The idea here is, and these are not that bad in most cases, what will happen is there will be a weakness in the body wall somewhere, And when you're doing something like heavy lifting, or you're in a car wreck or something along those lines, the intestines in particular can push through the body wall and be found underneath the skin as opposed to inside the abdominal muscle. All right, this is very traditional. This normally is confirmed with imaging. There can be situations where you get what are called strangulations, where the body wall constricts the intestine so much that it can go into necrosis, can die. But normally it kind of moves in and out, if you will. Now, there are several different types of hernias. I will talk about a few of these which I feel are pertinent. First being inguinal hernias. Congratulations, ladies. This is not anything you have to worry about. Gentlemen, you will get hernias far more often than ladies will. All right, and the reason for this is based off of the way that the structure of the reproductive system is in males. In males, the testis, which again makes sperm, has to be made at a lower temperature than body weight. Wait, let me try that again. Sperm has to be made at a lower temperature than body temperature, so the testis are held externally in the scrotal sac. Now, what this means is that there has to be a means of conveying sperm from the testis back into the body where they are then possibly used elsewhere. To do this, we have to have openings in the abdominal wall, in the lower abdominal wall, called the inguinal canals or the inguinal rings. These are two little openings that allow for the spermatic cords to re-enter into the abdominal cavity, to go into the pelvic cavity. And these are weaknesses. They're inset weaknesses in the abdominal wall. So what you get are what are called inguinal hernias, where parts of the intestine protrude through the inguinal canals, protrude through these inguinal rings, and in really bad situations can actually make the intestines can actually make their way all the way down into the scrotal sac. I've heard terrible examples of people doing like powerlifting at competitions and blowing intestines down into their scrotal sacs. It's a terrible thing. All right, hiatal hernias. Hiatal hernias are very prevalent amongst people who are dramatically overweight. What will happen is you have all of this weight buildup in the abdominal cavity, and that pushes up against the stomach, and that slowly pushes the stomach through the diaphragm up into the thoracic cavity. So, in other words, you have the diaphragm here kind of constricting the top uppermost portion of the stomach. And normally what will happen here is if you eat a big meal and you're trying to breathe, it's going to squeeze at the stomach and you're going to have really bad acid reflux as a result. So that's a hiatal hernia. Umbilical hernias, man, super common on newborns. Super common. A newborn, they have an umbilical cord which is not fully formed. The abdominal wall is not formed there yet, so parts of the intestine push their way into the degrading belly button, the umbilical cord, and you end up with a little red spot on the end of their what will become their belly button. And this normally goes away by the time kids are about 7 years old. So the abdominal wall slowly creeps in and overtakes it. And then last but not least are diaphragmatic hernias. Diaphragmatic hernias are incredibly rare. Again, there's lots of different forms of hernias. I just put diaphragmatic hernias on here for one simple reason, and that's because I have a crazy picture of one. Diaphragmatic hernias are where abdominal organs are found in the thoracic cavity. So here's a cat dissection. This is just a normal cat dissection. You've got the thoracic cavity and the abdominal cavity. There's the diaphragm, heart and lungs, intestines and liver. It's all there. Here is what I found one day when I was doing dissections at UA. So what you see there is the diaphragm and the liver. The small intestines are up in the thoracic cavity. And that's crazy. That's not the way this is supposed to be by any stretch of the imagination. When you pull the intestines out of the way, the heart was pressed so hard into the left rib cage that you can see the outline of the heart like a lump on the outside of the body. The right lung was vestigial. It wasn't even there. The left lung was about a third the size it's supposed to be. This was a full-grown adult cat, but I don't know how it survived. Especially not really being able to breathe. So having like 1/6 lung capacity is pretty wild. That's a wild number. It's probably the laziest cat that anybody's ever seen. And when I say lazy, I mean it probably had no energy to move. Alright. Muscle compartments. So in areas where your muscles come into contact with one another, and especially when your muscles, like the ones that run the fingers, you have a lot of muscles in a small area and they've got a lot of tendons around. What you'll do is you will compartmentalize those areas of the body so that the muscles can move freely and independently of one another. So you have muscle compartments that enclose muscles so they can act independently of other muscles. Intermuscular septa separating one compartment from another. So we have muscles in their own little compartments, and it works great. This is the way it's supposed to work. It's good. There's not a problem here unless you're in like a car wreck or something like that, in which case you can come down with what's called compartment syndrome. If you're in a car wreck or you have some sort of blunt force trauma to like an arm or a leg or something along those lines, what can happen is the muscle can bleed internally to the compartment. And as the muscle bleeds in the compartment fills with blood and it becomes pressurized. And once you pressurize the compartment, it can no longer bring in more blood, which would bring oxygen, which would heal the tissue. So what you end up with is the muscle compartment completely full of blood, fully pressurized. Blood can't leave, so everything inside the compartment just dies from necrosis. It can't get oxygen, it just dies. Alright, and that's obviously very, very bad. I had a student years ago, and after I gave this lecture, she walks up and says, "Hey, I want to show you something." Pulls her sleeve up, and basically all she had was like the skin wrapped around bones in her arm. Because she was in a car wreck, and the doctors didn't catch it. She had compartment syndrome, and all of this muscle, all of it was gone. It was all gone. They had to remove it, because it all died. Alright, so let's see, what do I want to say here? Pressure, as you know. Okay, so if you're in a low blood flow, low oxygen situation for more than a couple of hours, the nerves begin to die. And after several hours, the muscles begin to die. This is very easily diagnosed. We call these the P's: pressure, pallor, pulse, and paralysis. Pressure, I can feel my muscles. And if like one strip down through here feels like a brick, like it's rock solid internally, that's a good example of compartment syndrome. Pallor. Like me and my Northern Scottish heritage, like I've got very, very light, pale skin, I would see a red line going down my arm. Like it would be a big bloody, underneath the skin, bruise underneath the arm. Very clear sign of compartment syndrome. Pulse. Anywhere there's an artery in your body, you can pick up a pulse. But if you can't find the pulse in a muscle, hey man, that's a good example of compartment syndrome. And then paralysis. Once the muscles lose blood flow, it's like you've fallen asleep on your arm, right? You wake up and the arm is numb and it doesn't want to work. That's classic paralysis. That's compartment syndrome. So if you're in a car wreck and your arm stops working, hey man, you need to get to the hospital, alright? Now, let's see, what do I want to say here? Muscle damage is permanent. The nerves in the peripheral nervous system, if you just damage part of an axon, like way down here as opposed to up in the spinal cord, there's a chance of healing it. And it's pretty easy to diagnose this through a blood test as well. Myoglobin, which is a form of hemoglobin found in muscles, is pretty unique, and it's supposed to stay exclusively in muscles. If you start seeing this in the bloodstream, very characteristic sign of major muscle damage internally. And that's a problem. Because if you're finding myoglobin in the bloodstream, that means it's going to the kidneys, and the kidneys can't cope with myoglobin. They can't figure out what to do with it, so it causes kidney failure. My friend that was, or my student, I should say, that was in my class that had her arm damaged so badly, she also was in the hospital for weeks with kidney failure. Alright, this is a real problem. It's referred to as rhabdomyolysis. Now, if the problem is that you got a muscle compartment that's full of blood, and it's pressurized, and you can't get more blood in, what's the obvious answer on how to fix this? Well, we do what's referred to as a fasciotomy. Fasciotomy is when we come in here and we cut the muscle compartment open, allow it to bleed, okay, let the blood out, and then the heart can pump in fresh blood and fresh blood and fresh blood and slowly heal it over time. It works just fine. So the people I know that have seen this done say it's quite a show. Okay, you get this big pressurized cavity, you slice it open and blood just goes everywhere. But it's better to do that than to die, which is obviously bad. Alright, shin splints. Do I want to talk about shin splints? So the idea here is that you can inflame tendons and their coverings. You can inflame the periosteum of your muscles. You can inflame the compartment at the front of the leg, for instance, with the tibialis anterior muscle, and this causes what we call shin splints. You can even get microfractures in the bones, what they call little stress fractures, and it can cause the legs to hurt. This is a classic runner situation. So if you've been pushing your legs too hard, you end up with shin splints, and this is basically just inflaming the muscle tendons, inflaming the muscle compartment, inflaming the periosteum of the bone itself. This is shin splints. Alright, now, I have included on this a quick review of some of the stuff that we've done previously. I invite you to look this over. I'm not going to run through it all with you at this particular time. I'll probably upload a review video and do that later on. So this is what I've got for you for now. It's a nice walk through this next chapter. It's basically the extent of what you need at this stage. And you'll be seeing some lab materials up from me probably next week. We're going to keep that simple as well. Alright, have a good day, folks.